Okay, well, welcome back to our Thursday video for this week. And we're in chapter 6. We're talking about the structure of the atom, which leads up to the idea of periodic properties, because of course the periodic table, as I've said before, is arranged the way it is because of the way the properties of elements vary in a repeating, predictable way. And the reason that that happens is because of the way their electrons are arranged. So before we can talk about the arrangement of the periodic table in any more detail than we already have, we have to talk about periodic properties. And before we can talk about them, we have to talk about the electronic structure of atoms, because that's what gives atoms their chemical properties. We just talked about line spectra and how classical mechanics, the kind of mechanics that Isaac Newton devised about 350 years ago or so, would predict that if you were to add energy to an atom, and that would, adding energies to anything basically makes it unstable, and that thing will then tend to release the energy in order to come back down to a more stable, lower energy situation. And so using Newton's laws of mechanics, we would expect that if we added energy to an atom and putting it into what's known as an excited state, which is unstable, the atom would then release the energy and come back down to a more stable or lower energy state. And we would expect that the energy released would be a broad spectrum of wavelengths of energy, or all different frequencies of electromagnetic radiation. In other words, if it happened in the visible range and you put the light through a prism to separate the light into its individual colors, what you should see, according to Newton, would be a rainbow, a continuous progression of colors from red to orange to yellow to green to blue to indigo to violet, with no separation between them. Each color would just bleed into the next. That's what Newton's or classical mechanics would predict. What actually happens, of course, though, is that you get a line spectrum, which is what we were talking about last time. The line spectrum, meaning that there are only certain narrow bands of individual wavelengths of electromagnetic radiation that will be given off as an atom releases energy. And that contradicts what Einstein said. And so what it means, basically what it means is that excited atoms, when they release energy, can only release certain amounts of energy. In other words, the energy that the atoms are able to release is quantized, meaning only certain values are allowed and other values are not allowed. And that was a real head scratcher for scientists in the late 19th century when this effect was first discovered, because, like I said, according to classical mechanics, that should not happen. So along about 1885, a guy named Johann Balmer came up with an empirical equation that would explain why these only certain energies are allowed, or at least it was an equation that fit the situation. The equation didn't really explain why only certain energies are allowed, but it allowed scientists to predict what energies would be allowed. Anyway, the equation works only for hydrogen, that is, or other things that have only one electron. And it relates the wavelengths of the lines, or basically the wavelengths of the electromagnetic energy that's released, to positive integers. And so his equation was that 1 over the wavelength is equal to some constant k times 1 over 4 minus 1 over n squared. So n is some positive integer greater than 2. So it could be 3, 4, 5, 6, whatever. And 4 is actually 2 squared, as it turns out. So you can think of this as 1 over 2 squared minus 1 over n squared, with n being whole numbers from 3 up. And with the right value for the constant, that actually gave you the wavelengths for the lines that you actually see in hydrogen. These were in the visible range. Okay, it turns out hydrogen also has a line spectrum in the infrared, and Balmer or somebody working with him also came up with an equation for that, which is 1 over wavelength is equal to some constant times 1 over 9, which actually turns out to be 1 over 3 squared, minus 1 over n squared. And n in this case is any whole number that's greater than 3. So the second number has to be bigger than, the second denominator has to be bigger than the first. Okay, and then it turns out, of course, there are also emission lines for hydrogen in the ultraviolet range. And you might wonder, okay, hydrogen's only got 1 electron each. How can there be so many emission lines? And I addressed this briefly in the last lecture, but that's because each hydrogen atom has 1 electron, and that 1 electron starts out in the lowest possible energy position. And when you add energy to the atom, that electron will jump out further from the nucleus to some higher energy position, like maybe here, or maybe here, and so on. When you stop adding the energy, the atom tends to release the energy, and the electron drops from a higher energy position to a lower energy position. But that lower energy position isn't necessarily the same position it came from originally. It could be some intermediate position. So like in this case, the electron could jump from the first orbit to the third orbit while you're adding energy, but then it could drop back to the second orbit, which would be an emission line. And then it could drop back to the first orbit, which would be another emission line. But then some other atom of hydrogen could drop directly from the third orbit to the first orbit, which would be yet another emission line, and so on. And in any sample of hydrogen, you're going to have a huge number of hydrogen atoms. So essentially, there are a whole bunch of different transitions that are going on at the same time. Only one transition at a time will be going on within any one hydrogen atom, but you've got a whole lot of hydrogen atoms. And so there are a lot of possible different transitions. Some of the ones that only emit a little bit of energy happen in the infrared, and some of them that emit a lot of energy happen in the ultraviolet, and some that emit moderate amount of energy would occur in the visible range, and those are the lines that we can actually see. Okay. A few years later came a scientist by the name of Johannes Rydberg, and Rydberg actually managed to basically find a constant and a version of this formula that would fit all of the emission lines for hydrogen. So his equation is that 1 over lambda, that is 1 over the wavelength of the line that's being emitted, would be equal to the Rydberg constant, which is actually R with a subscript of the infinity symbol, but you can just call it ρ if you like. I like to call it that because it looks like ρ. Times 1 over n1 squared minus 1 over n2 squared. So ρ, again, is the Rydberg constant. That turns out to be 1.097 times 10 to the 7th, and the unit would be meters to the minus 1. And that's because the equation is actually going to give you 1 over wavelength. Sorry, and n1 and n2 are positive integers, with the condition that n2 has to be bigger than n1. Okay. And so the n numbers just represent the number of the orbit that the electron is coming to or coming from or going to, with the lowest energy position where the electrons in hydrogen start out being n equals 1, and then the next lowest energy orbit being n equals 2, and the next lowest being n equals 3, and so on. And theoretically, an atom like even hydrogen could have practically an infinite number of orbits. So, the higher number for the positive integer could theoretically be practically anything. once you get it, now, of course, in practice, once the electron is a certain distance away from the nucleus, that electron will no longer feel any attraction from the positively charged nucleus, and the electron effectively doesn't belong to that atom anymore, and it's a free electron. But in theory, anyway, the n can go up as high as infinity, or at least a very large number. Now, this equation here still only works for hydrogen. With a different constant, it can actually work for any other thing that has one electron. So, hydrogen atoms have one electron each. A helium plus ion has one electron each. A helium atom normally has 2 electrons, but if it loses an electron, it becomes an He plus ion and only has 1 electron. So this equation would work for that also, but the constant would be different. Okay. Sorry. As impressive as this realization was, that well, actually, it's a fairly simple equation, but realizing it, coming up with it based on their observations of line spectra was actually a pretty impressive feat. Even so, they've only managed, to this day, they've only managed to do it for hydrogen and other 1 electron species like He plus. Once you add a second electron, things become infinitely more complicated. And that was actually another thing that contradicted classical physics, in that in classical physics, the electrons should not interact with each other. But in real life, they do. And that's what makes the line spectra of things with 2 or more electrons so much more complicated. And like I said, even to this day in the 21st century, we haven't come up with a similar equation for anything with more than 1 electron. This, what this really meant was not actually understood by Rydberg. He didn't understand how this equation applied to the atom. That was left to Niels Bohr in 1913. Bohr came up with his model of the atom, which is what I drew here, and only then were they able to relate, okay, this is why that equation is the way it is. Because it was Bohr that theorized the existence of orbits with their energies depending on how far the electrons are from the nucleus. Okay, so that brings us to the Bohr model of the atom, which is the second section of chapter 6. Before we get to Bohr, we get to Ernest Rutherford in the 1890s, or 80s, 1880s or 90s anyway. And for Rutherford, an atom consisted of a small, heavy, positively charged nucleus surrounded by very small, lightweight, negatively charged electrons. And the distance between the electrons and the nucleus was relatively large compared to the size of the nucleus and the electrons. I think it was Rutherford who discovered that a vast majority of the volume in an atom is actually empty space by doing his gold foil experiment, where he shot helium nuclei at a gold foil and found that most of them went right through with no problem, which really wouldn't happen if atoms were little billiard balls as previous scientists had envisioned them. So he realized that there must be some very small but heavy positively charged mass at the center of the atom, which is the nucleus, and that any negative charges were dispersed outside the nucleus, but at large distances from the nucleus and large distances from each other. I think I mentioned once before, if we were able to blow up an atom to the point where the nucleus was the size of a basketball, and if we were in our usual classroom at Villa, and I had the basketball-sized nucleus on the podium in front of me up at the front of the room, the closest electrons to that nucleus would probably be somewhere around the Galleria parking lot. So that, it's a huge, huge distance between the nucleus and the first shell or the first orbit of electrons. And it's a huge distance between those electrons and the electrons in the second orbit, and so on and so on and so on. Rutherford came up with the idea that the electrons were in orbits around the nucleus, and also that the number of positively charged particles, I don't think they called them protons yet, but the number of positively charged particles had to be equal to the number of negatively charged particles. And the neutrons though were not known yet. So there was some mass in the nucleus at the time that was unaccounted for. And it wasn't until neutrons were discovered, I think in the 1930s, that they finally discovered where, what was responsible for that unexplained mass. Rutherford's model was known as the planetary model because it had the nucleus at the center, similar to the sun at the center of the solar system, and the electrons revolving around the nucleus, sort of like the planets revolving around the sun. Classical mechanics said that if electrons are moving in a circular orbit around the nucleus, then it's constantly accelerating. Because if you take physics, when it's offered here at Villa or somewhere else, you'll learn that in physics anyway, acceleration is considered to be a change in velocity. And velocity is not just speed in physics. Velocity is speed and direction. So say if you're racing, if you're having a car race on a perfectly circular track, you can keep going the same speed the whole time, but yet you're constantly accelerating because you're constantly changing direction if it's a circular track. And the same kind of idea would apply to electrons in an atom. If the electrons in an atom are traveling in circular orbits around the nucleus, then they are constantly accelerating because they're changing direction. Even if their speed doesn't change, they're changing direction. That means that they should be constantly emitting energy in the form of electromagnetic radiation. But they're not. Okay, and what that also means is that loss of energy by the electrons through the emission of electromagnetic radiation should make the orbits continually smaller. So in other words, over time, classical mechanics would lead to the conclusion that the electrons in every atom should eventually come crashing into the nucleus. But yet we know they don't. So there's got to be more there than what's envisioned in classical physics. So again, that's another reason that scientists had to come up with new theories for why atoms and subatomic particles behave the way they do. Okay, so in other words, according to classical mechanics, the atom, as scientists knew it to be arranged by about 1900, would be totally unstable. And so therefore substances, anything made up of atoms, which is literally everything, should be constantly changing, constantly emitting energy and going to a lower energy state and changing. But that's not true. And so along comes Bohr to try to explain that. And what he did is he combined classical ideas with Planck's idea of quantization of energy and Einstein's idea of photons being particles. Okay, so he brought together classical ideas along with the wave-particle duality. And he came up with what's known as the stationary state hypothesis, and that is electrons orbiting a nucleus in a circular orbit emit no electromagnetic radiation, but they would emit or absorb electromagnetic radiation if it moves to a different orbit. So as long as an electron is going around and around in the same orbit, it does not absorb or release any energy. But if it moves to another orbit, it does absorb or release energy. If the electron moves to an orbit farther away from the nucleus, it absorbs energy. If it moves to an orbit closer to the nucleus, then it releases energy. And because in any given element, the orbits are in fixed locations, according to Bohr, that means that the orbits have fixed energies, and the electrons can only reside in an orbit. You can't have an electron that's halfway between one orbit and the next, unless it's in transit from one orbit to the next, and then it would be only between them momentarily. So there are only certain levels of energy allowed for the electrons. And so when an electron makes a transition and emits electromagnetic radiation, it'll emit a certain amount of energy or a certain wavelength or a certain frequency, depending on how you want to look at it, based on the difference in energy between the two orbits that the electron is transitioning between. And again, since those orbits can only exist in certain locations, only certain differences in energy are allowed. And therefore, only certain wavelengths of electromagnetic radiation can be emitted. And that was a very elegant theory, and it explained just about all of the problems that were known with the theories at the time with the structure of the atom. Although as time went on, other problems arose which required an even fancier explanation, and that will be quantum mechanics, which we'll get to next. So we're sort of building our way up to quantum mechanics. Okay, so an electron needs to move to a different orbit in order to absorb or emit energy. And emission of electromagnetic radiation means the emission of photons. Basically, one electron undergoing one transition will either absorb or release one photon. So each transition from a higher energy position to a lower energy transition releases one photon. Now, one photon is really, really tiny. It's so tiny that it's not even considered to have a mass. But in any given sample, say like in a hydrogen lamp, you're going to have, billions and billions and trillions of hydrogen atoms. So it's entirely possible that you'll be releasing a whole lot of photons all at the same time. And that way we get enough light that we can actually see it and measure it. Absorption of electromagnetic radiation by an atom, or actually, basically any kind of energy, means absorption of a photon. Each orbit has its own energy because and that energy is based on how far away it is from the nucleus. And each transition between one orbit and another orbit will have its own value for delta E, or change in energy, and therefore it'll have its own characteristic wavelength and its own characteristic frequency. Because different atoms have different numbers of electrons, and also different atoms will have orbits that are different distances away from each other, and because there are different numbers of protons in the nucleus, that means that the orbits in different elements will have different energies, and therefore the transitions between those orbits will have different energies, versus other elements. And that's why you can get a unique spectrum for each individual element. So an electron moving from one orbit to another will have a change or difference in energy that's equal to the energy of the final location, whatever orbit it ends up in, minus the energy that it had in its initial orbit, which is equal to h nu, that is Planck's constant times the frequency in hertz, or hc over lambda, that is Planck's constant times the speed of light divided by the wavelength in meters. Okay, the nu, that is frequency, and lambda for wavelength refer to the electromagnetic radiation that's emitted or absorbed. And EF and EI are the final and initial orbit energies. Okay, this equation doesn't allow continuous values for energy. And again, that's based on the fact that the electron can only reside in certain defined orbits and not just anywhere in between them. The energy of electron in an orbit with a number n for hydrogen is E sub n. That's energy of an electron in orbit number n. Again, with the first one being n equals 1 and the second one being n equals 2 and so on, is equal to negative k over n squared. And k in this case is a constant that sort of brings together the electron mass, the electron charge, and Planck's constant And that constant K in this case is actually 2.18 times 10 to the minus 18 joules. And N would be some positive integer, 1, 2, 3, whatever the orbit number the electron is in happens to be. Again, this is for hydrogen. Notice this means that the energies in any given orbit will be negative. And for n equals 1, n squared, of course, would be 1. And so the energy of an electron in n equals 1 is just 2.18 times 10 to the minus 18. As n becomes larger, the energy becomes smaller and smaller, but it's still negative. And so what happens is the lowest energy is an electron in n equals 1, and that's the lowest energy because it's a large negative number. In n equals 2, the energy is still negative, but it's a smaller negative number, which means that it's actually greater than the energy in n equals 1. And the energy in n equals 3 is still negative, but it's a smaller, it's a smaller negative number, which makes it larger than the energy in n equals 2, and so on. So essentially, the energies get less and less and less negative as you go further out from the nucleus. And the maximum energy for the electron would be 0 when it reaches an infinite distance from the nucleus, because when it reaches an infinite distance from the nucleus, then essentially the atom or the electron doesn't belong to that atom anymore. It's just a free electron completely independent of the atom. Okay, the energy for changing orbits in hydrogen is given by this equation. The change in energy when an electron makes a transition between two orbits is just K, again, this constant here, times 1 over n1 squared minus 1 over n2 squared. And that is equal to hc over lambda. Or you can look at it in the form of the Rydberg equation, and that's 1 over the wavelength that would be absorbed or emitted as a result of this transition is equal to K divided by hc. And K over hc is just the Rydberg constant, by the way. So this is ρ, or R infinity, which is 1.07 or 1.097 times 10 to the minus 7 meters to the minus 1, times 1 over n1 squared minus 1 over n2 squared. So this brings us back to the Rydberg equation, actually. And as I mentioned a moment ago, the orbit nearest to the nucleus is the lowest in energy, meaning it has the largest negative number for energy. And that's considered n equals 1. And the energy for n equals 2, n equals 3, n equals 4, basically they get less and less and less negative until finally culminating in n equals 0, or E equals 0 at n equals infinity. So the energy in n equals 1 in hydrogen of an electron would be negative 2.18 times 10 to the minus 18 joules. Sorry. The energy of an electron in n equals 2 in hydrogen would be negative 5.45 times 10 to the minus 19. This is a smaller number because it's minus 19 than the energy in n equals 1. So the number is smaller, but it's negative, which actually makes it bigger. So negative 5.45 times 10 to the minus 19 is actually bigger than negative 2.18 times 10 to the minus 18. And then the energy of an electron in n equals 10 would be negative 2.18 times 10 to the minus 20. And again, 2.18 times 10 to the minus 20 is smaller than either of these numbers, but when you make it negative, that means it's actually bigger because it's a smaller negative number, or in other words, it's less negative. So you're approaching 0 from below. All right. I see we've gone a little over the limit for the first segment, so I'm going to call it there, and we'll pick up here when we continue.